Chancellor for Research for the University of Missouri in Columbia. And after we have Dr. Andrea Aparo, that is professor at the University Sapienza in Rome, as well as at the Polytechnic in Milan. We have another professor in physics, Professor Takahashi, that is an emeritus professor at the Osaka University. We have Frank Gordon, that is a former US Navy officer, and after 38 years of service at the Navy Research Labs, is also co-chairman of the International Conference for Cold Fusion that will be held in Korea a few days from now. And finally, last but not least, Michael McKubre, that is the director of Energy Research Center at the Stanford Research International in Stanford. So gentlemen, thank you so much for having accepted this challenging task to have a panel on anomalous heat effect, and thank you for being here in Austin. Professor, it's yours.
If I could have the first slide, or is there something to advance? Is there?
I think it's this thing.
Oh, great. Super. Thanks a lot. Appreciate it. Well, what I was hoping to do as we start out today is take you back about 24 years ago to a situation that many of you may remember. It was March 22nd, 1989, a news conference in the University of Utah, and Fleischmann and Pons announced cold fusion, and this created a huge excitement. Well, actually, the story starts well before that, in 1926 in Berlin, when two Austrian physicists, Paneth and Peters, announced that apparently their hydrogen that was absorbed in palladium joined to create helium. And this was well before we knew about deuterium, this was well before we knew about nuclear fusion. But this report was so exciting that the ensuing discussion in the Berlin science community later resulted in a retraction by Paneth and Peters, but the first appearance of an interesting anomaly. Now, we had heard earlier today about a wonderful description of the National Ignition Facility. This is an example of hot fusion, where the particles are hot enough that by collision they sometimes exceed their Coulomb barrier and fuse. Actually, in the mid-1950s, there was a very big discovery in Russia and in the United States of a subnuclear particle called the muon, subatomic particle, that could actually catalyze the fusion of deuterons to form helium. And this is very well established, but it's led to years of questioning whether there's some aspect of the condensed matter state that might actually be able to form such a catalysis. Well, that was the stage that was set in 1989 with Fleischmann and Pons' announcement. And the interesting result of this was that many people charged in to try to repeat these results. And since many people were trying to do an extremely difficult experiment, it's no big surprise that repetition was an issue. So I think quite incorrectly and inappropriately, this was discredited because, again, the immediate attempts of many experimentalists in 1989 to reproduce the results of Fleischmann and Pons were unsuccessful. Now, as Scott Pelley said in 60 Minutes, a strange thing happened on the way to oblivion. Everyone thought that this was just dead. But since that time, there have been over 200 reports, very credible, of excess heat from many different groups that are similar to the Pons and Fleischmann results. In fact, this has been seen and in fact verified now by 3 national laboratories, the Navy labs in the United States, NEA, the National Energy and Environment Lab in Italy, and the national laboratories in India. So there's been quite a bit that now causes us to realize this is actually something that's to be very much considered. Now, it's interesting, this has been seen in various systems like hydrogen and nickel, deuterium, which is heavy hydrogen, and palladium, and in some other systems. And these are displaying no measured radiation in many occasions. And also, obviously, since no carbon's involved, no carbon emissions. So naturally, this is an area of great excitement if, in fact, this is a new source of energy that we've been overlooking. And since we now have the confirmation from many national labs that this excess heat effect is in fact real, it really deserves very intense study. Now, there are different loading modalities to get the hydrogen in, including electrochemical, which was Pons and Fleischmann's original discharge, co-deposition, where you just grow the hydrogen in the metal itself by deposition, and gas diffusion. And there are also a number of working devices now that are showing this excess heat. In fact, you'll see some on the exhibit room floor. Very exciting results that are here at this meeting. So it's interesting because when you look at the level of heat release from these very, very small structures, it's much more intense than what you'd expect from the enthalpies of a chemical reaction, often by a factor of 1,000 or 10,000. So again, this deserves really, really close study, and it's been receiving close study by many dedicated people, such as people on the stage, but really this should go to a new level, in my opinion. So what's going on? Simply, we don't know, and it's likely going to take a number of years of very carefully controlled experiments following strictly the scientific method to figure this out. But the excess heat is real, and that is confirmed by many. So this, again, motivates greater scientific investment, in my opinion. Is it a nuclear process? Possibly cold fusion. If so, look for the byproducts like helium. Is it low-energy nuclear reactions, an electroweak process? If so, look for effects of neutrons. Again, these both have been posited. Could it be something else or multiple mechanisms? Okay? I propose calling it the anomalous heat effect, AHE, until we know more about the actual underlying mechanism. Now, one thing that I think is really critical to ask is what's different now from what was observed in 1989 when many experimentalists rushed in and failed to repeat Fleischmann and Pons. And I think the most telling is this outstanding work by Michael McKubre. And so, Michael, maybe we go to you first to discuss what's different now than in 1989.
Well, thanks, Rob. I'm going to add another personal milestone. My group at SRI had been working on the deuterium-palladium system for about a decade before the 1989 announcement by Fleischmann and Pons, and for different reasons. We were developing a hydrogen sensor for use in the pressurized water systems of conventional nuclear power systems, and we happened to be working with the Canadians and their CANDU reactors, which are heavy water reactors. So our sensor was palladium, the environment was heavy water, so we had a lot of expertise in understanding how hydrogen or deuterium enters into the palladium, and we had more experience probably than anybody else at that point, and we're in a better position to know that the claims that Fleischmann and Pons were making were unlikely, or at least occurred in a very rarefied environment, since we hadn't seen any excess heat, and we'd been studying this quite closely for about a decade. Excuse me. So the conjecture was then that if Martin is right, and Martin was probably the most able experimentalist I've ever worked with, if Martin was right, then this effect had to be occurring in a regime of loading of deuterium into palladium that was not normally accessed. So we set out as a task in my group to understand how you could get large amounts of deuterium to enter into the palladium lattice, and how to measure it when it was in there. So this was, just that activity alone was probably a 6-person year effort over a couple of years. And the curve that Rob is showing here is the result of that effort, or one of the outcomes of that effort. Turns out that the effect, excess heat, anomalous excess heat, as Rob has described it, occurs only if you exceed a threshold in loading. There are other thresholds as well, but you need to exceed that threshold and maintain that loading for a considerable period of time. So there was a hitherto unexplored regime, but we later came to understand that simple failure to meet this loading threshold, and it was a very difficult thing to do, a simple failure to meet this loading threshold resulted in a lot of the stories of irreproducibility. There wasn't an irreproducibility of effect, there was an irreproducibility of condition. You needed to get the conditions right in order to expect to see the effect. And unfortunately, this had consequences. Some very prestigious laboratories and very able electrochemists at MIT, at Caltech, and Harwell in England did quite prominent research, put a considerable amount of effort into it, were not able to see the heat effect, and reported decided that it's not there, it's probably wrong. And now we know, with the benefit of 2020 hindsight, or the gentleman this morning in the lecture, 2015 hindsight, or even better, now we know that they could not have seen the effect. They didn't meet the conditions, the minimum set of conditions necessary to produce the effect. So this was a long story and a long tale, and eventually, by about 1995, we had diagnosed the minimum set of conditions necessary to produce the effect. It's a multi-threshold phenomenon, and I have an empirical equation which I'm slightly ashamed of, in that it's a very stupid equation. It just happens to describe the circumstances of excess heat production in electrochemical loading of deuterium into palladium, and it allows us to explain our failures now. We have an equation which says if you don't meet these conditions, you will not see the effect, and you can learn this way from your failures.
Wonderful. Thanks a lot, Mike. Really exciting, this progression that's led since 1989. And this has become very much an international endeavor. And there have been, again, acceptances and experiments conducted on every continent, and it's been a very exciting time. To that end, too, I thought maybe, Andrea, could you please describe to us more the priorities in the European Union and their material synthesis that will incorporate this in the future?
Well, sure. You know, the Europeans are on the other side of the ocean. They're a little bit slow usually, especially seen from this side of the ocean, but we get there. And so on October 28th last year, there was a meeting in Brussels organized by the European Commission, and the issue that they discussed then, with the official title was Forward-Looking Workshop on Materials for Emerging Energy Technologies. And the result of that work was that they came up with a report under the was published by the Director General for Research and Innovation. And what they say in that report is that the low energy, or whatever we want to name it, I like the quantum reactor. It sounds very much like Star Trek, but anyway, for me it's fine. I would like to call it what the hell it is, but the American version will be, let's see, WTHI squared. If you don't use acronyms, you're not happy on this side of the ocean. So, that's fine with me. So the point is that they have included the LENR as a research team. They have explicitly said that the Framework Program 7, which is it's the General Program for Research of the European Commission, has to be to make calls on research on materials and support study of material science as a strategic approach towards this kind of issue. So the point is that what really the politicians are saying is quite simple. They are saying, do your work, you're scientists, apply the scientific method, but without prejudices, please, and go where the data leads you, and we will not follow you. We will walk with you toward that direction. It's no more the time to have a separation between basic research, applied research, industrial application, whatever. We don't have the time, by the way, and it's a waste of resources. So the point is that what the EC is saying at this point is the European Parliament. We had a hearing a couple of months ago, and they were just asking us to tell them why there is an interest. And the reason why what we showed them is very simple: data, factual data. And that's more than enough to convince people.
And sticking to the international theme and how this discovery is occurring throughout the globe, Akito, of course, your work and the work of like Professor Arata, who's twice recipient of the gold medal from the Emperor, have really pointed to some very exciting results. Could you share those with us?
Yes, Arata is such a special series from Japan. Let me highlight my experience first, because I think this cold fusion is very crazy. I was very exciting researchers. And in my personal experience, when freshman course announced the astronomic strings in 1989, I was involved in making a service for hot fusion team for providing the nuclear data for DT reaction, for tokamak and Energia confinement, like Livermore machine, or Osaka University and also laser implosion fusion machine. So I was working so I thought the claim to excess heat without neutron emission was very crazy, probably impossibly explained by non-nuclear physics, by two-body interaction. So I thought if it were true, that must be something like multi-body interaction, three-body, four-body nuclear interaction must be involved because of the constraint or ordering or self-organization process in condensed matter. It's the only reason to have something new, physically. So I didn't have time involved in research at that time. However, eventually we had a Tiananmen crisis in China that made me to have a chance to do. Because we had, at that time we had a trilateral project in hot fusion to do from Japan and China and the United States. But that interrupted our fire, so I had a chance to do experiment. And I was a specialist in neutron measurement. So I started to measure neutron if it happened in my heavy water electrolysis with cathode or titanium even. And I didn't see anything happening, but I tried to see changing the conditions and so on. And eventually I found a little bit of neutron English. And I was a specialist of neutron physics, so I could define that was the really 2.45, 45 MeV neutron from DD reaction, a little bit. So I was very much excited, and something happened. So, well, our phenomena is not so repeatable. We don't know the repeatable condition. So I was involved in that very much. So I repeat the experiment and try to find the neutron event repeatedly. Very difficult. Very eventually, by chance, that came different things, like excess heat coming out of my experimental device, cells, over 100 watts excess, with the input about 100 watts. So exciting, using some special kind of electricity, high current, low current current operation and so on. And we found some correlation with neutron level, so we was very excited. And so some people like over there and Francesco Celani from Italy started to repeat her result using the same batch of palladium material. They said they could repeat some. But after that, we have no spare of palladium with the same batch, and we used a new batch. So we didn't find anything anymore. Disappeared. Not come back. Strange. Once we saw such very anomalous results, we cannot stop. So there should be something we have to investigate, to find, elucidate what's going on. That's very. I think that was also the triggering point to start the Japanese governmental project. NHE project so-called. That's a new hydrogen energy project. We set up the laboratory in Aparo, and we invited also US and European scientists there, and want to repeat the freshman course experiment using his device. But unfortunately, we couldn't reproduce well. We tried many things in metallurgical point of view, or hydrogen loading, also changing the condition and so on, but very difficult to find. So, finally, the project was terminated. That became a very big trouble to us, because after that, all the Japanese governmental fund to cold fusion research was cut. Zero, just zero. So how we can continue this? Because some people found some accidental results showing this positive, but not repeatable. Okay. However, our Japanese people continued without money, using maybe private money or something, and cheating money from some laboratory.
It is still money.
Still money,
Yeah.
money and manpower. That can be a sales problem. And so after some years, one professor in Osaka University suggested maybe we might use atomic cluster of very small nanoparticle and isolate it in some ceramic machines. That will make the particle working very typically and avoiding the getting together electric particle. And maybe repeatable phenomenon might happen. So the Arata-san used that idea and we started the experiment, found very nice results. So after my retirement, I had a chance to repeat the experiment by support of some a little bit company, Technova, incorporation, and we settled this small laboratory in Kobe University. Professor Kitamura started that job with gas loading, nanoparticle, and nanocomposite material. And now we are seeing very beautiful results with that.
And did you get back the money from the Japanese government?
No,
Too bad.
too bad. So we need support from some other company, from Japanese government to get that.
Very exciting. And in fact, I think this is a trend where, of course, science funding is an issue
So
throughout.
some scientific results are status now. I'll make a presentation tomorrow afternoon.
Very good. Excellent. Very nice. Well, I think this is kind of a common thread, too, because, of course, science funding is difficult today, more so than before. And I might go to Frank, too, and ask, Frank, before he retired, was with the Navy SPAWAR lab in San Diego and sustained for many years a very successful research program there. So, Frank, how did it go? Any thoughts?
Thank you, Rob. I'm a civilian scientist at the Navy lab, an R&D lab in San Diego. And in 1989, I was the head of the anti-submarine warfare department and had two electrochemists who were developing high energy density batteries for torpedo propulsion. It turned out they knew Flashman. And in fact, Flashman and Pons had been funded some by the Office of Naval Research prior to their announcement in 1989. So we were a little bit aware of what they were doing. And like thousands of people around the world, we went into the lab and started pulling bottles of deuterium and palladium and whatever we could find off the shelves and started doing an experiment. And one of the first experiments we did was co-deposition, which Rob mentioned earlier, where actually deposit palladium onto the cathode, and on the cathode is also where the deuterium evolves. And so you're building up a loading factor that is so important. And what we would see was that the cathode would be warmer than the solution. And it was very easy. We could actually epoxy a thermocouple right to the back of the cathode, have another in the solution, and consistently the cathode would be 2 to 3 degrees centigrade warmer than the solution. And that should not be. That's a real simple experiment, but that should not be. Joule heating would say that the solution should be warmer. So that was the first experiment that kind of set the hook, if you will. And for the next 23 years, we have been conducting experiments. One of the things that was extremely important to our research was following the scientific method. The Navy's a big organization. They don't want someone out doing experiments and making claims that will embarrass them. And so, they would ask, what are you doing? How can you do this? And I said, this is the experiment we did, and these are the results we got. And we published that paper. And then we did additional experiments, got additional results, and we published those papers. And over the course of time, we published 27 papers in peer-reviewed journals. And those papers document excess heat, production of X-rays, soft X-rays, production of hotspots, transmutations, obviously nuclear events of some sort, and production of particles, including alphas and neutrons. So, at every time, where I was asked, are you leaning too far forward, I would say, these are experiments we did, these are the results we got, and we have published the results. And that has served us well during the time that we were doing that. So that was extremely saying, you know, experiments aren't repeatable. Well, the community at large, I think, has increased repeatability significantly. There aren't any published papers. In addition to the ones we have, we were talking earlier, we think there's probably at least 1,000 to maybe 3,000 or 4,000 papers in peer-reviewed journals, not counting presentations at conferences and things like that. They said, you know, if it's nuclear, where are the neutrons? And, well, now we have discovered that there are neutrons. And then, you know, they said it doesn't match theory. And it still doesn't match theory. And in fact, one of the theories it doesn't match is it doesn't produce as many neutrons as theory predicts it should, which is fortunate for us because otherwise I think we'd all be dead. That was one of the statements that was made also. If this was really nuclear, you're producing neutrons and you'd have dead graduate students around. So fortunately for us, it doesn't produce the level of neutrons. In fact, estimates are it's about 6 or 7 orders of magnitude less than what you would expect.
Wow. No, I think this is a key point. The application strictly of the scientific method is, Dr. T said this morning in the keynote address, that this method of Galileo, this process of proposing a hypothesis, then detailing it more theoretically, and to that end, it's good to mention that Professor Peter Hagelstein from MIT has been involved in developing a very careful theory based upon time-dependent quantum perturbation theory to suggest why we occasionally see nuclear radiation, but quite often don't see nuclear radiation in these experiments. Of course, that's exciting in its own right, because that suggests that once we understand, following the scientific method, what this is coming from, we may find, again, an approach that would give a radiation-free process that's releasing energy far beyond chemical, which is very exciting. And so, Mike, any other thoughts in terms of...
Well, the expectation was set, I think, unfortunately, in the use of the term fusion, and fusion means different things to different people. When Frank was talking about the expectation of neutrons, that's from a particular reaction, a binary reaction where two deuterons somehow, usually by brute force, overcome the Coulomb barrier and bang into each other. And simple conservation of energy and angular momentum requires that you get energetic particles, you get neutrons, you get tritium. So whatever the process was that Martin Fleischmann and Stanley Pons discovered, it wasn't cold hot fusion. It was something else. And as we've developed in our experimental understandings and our theoretical understandings too, what is quite clear is that this invention of Martin Fleischmann and Stanley Pons is much bigger than they imagined it to be. What they've demonstrated in the subsequent experiments and the theories that are coming close to fruition now, what is demonstrated is that nuclear effects take place in crystalline bodies, in metal lattices, and possibly also in any form of condensed matter. Nuclear processes take place differently in condensed matter than they do in the rarefied environment of plasmas or essentially vacuum state. This is a huge statement. Something about nuclear physics needs to be fundamentally interrogated and reevaluated. I work at Stanford Research Institute, which is just across the kitty corner to Stanford University, and occasionally Edward Teller would summon me to his office, and you don't turn down a summons from Edward Teller. So he'd summon me to his office and ask me to explain myself. And we talk, and he was very attentive. Some of the time he was very attentive and brilliant too. But at the end he said, well, you haven't convinced me yet, but if what you say is true, it would take a very small change of the laws of nuclear physics as I understand them to explain this effect. So from a man who had written many of the laws and developed many of the equations which are then dumbed down and simplified and put into textbooks to teach our children with, the people that developed this work originally understood that there were things missing. And some of the things missing in Teller's mind would be capable of explaining this phenomenon. And he said to me two things which I ignored, I'm sorry to say. One was that this, if it turns out to be true, it will be an example of nuclear catalysis at an interface. I now believe that this is an example of nuclear catalysis at an interface, and I could have had this understanding if I'd simply trusted Edward Teller, 15 years ago. The other thing he told me to do was to go away and make my experiments as a function of the ratio of deuterium to hydrogen in the electrolytic system. Change the D to H ratio. And come back to him and report the results. And I didn't do that. And I should have done that. And had I done that, then we would have been well in advance of the situation that we find ourselves in.
Well, it's interesting, too, because this interest and this theme that Mike's been mentioning was an area of Julian Schwinger's interest, too. Unfortunately, he's passed away. But he was also very interested in this differing environment in which the potential fusion reaction occurs. And again, I'd like to stress that this is a fascinating anomalous effect. It'll be quite some time before we really understand fully the origins. So being able to entertain many mutually exclusive hypotheses and going where the data leads you, the Galilean method, the scientific method, certainly is a wonderful approach.
Well, there's also a great message in what you were saying to the graduate students. Respect your teachers, even if they are old.
Since I'm becoming to resemble that, I say especially if they're all.
Well, very good. And you know, what I'd like to do, if I could, just to try to kind of flesh out and give an opportunity for a broader discussion, would be that now we're in a situation where there's an anomalous effect that we all understand is real. 3 national labs have confirmed that. And of course, that leads to opportunities in translational research to try to take advantage and pragmatically applying that anomalous heat. And in fact, many companies are. And in a sense, they have something that's controllable. The fact they don't understand the origin is not a huge concern. But the situation is, once we understand, and once translational research works so seamlessly with fundamental research, hopefully understanding the mechanism will lead us to new manifestations experimentally that we haven't even thought of yet, because we haven't gotten that far down the road. But at this point, what I'd like to do is open this to the broader community for discussion. Certainly we have a number of people that have been involved in some early stage commercialization efforts. It's very exciting. Obviously we have a anomalous heat effect apparatus running on the executive floor of this outstanding National Instruments Week. So maybe with that, would anyone like to jump in, ask questions of the panel, or add to what was said so far? Yes. So I don't know, do we have a microphone? Pass on.
Yeah, whoops, sorry. So, hi Mike. In Rome, we presented a paper that
It's Rome, Italy, not Rome, Texas.
that's true. Okay, I'm Jonathan Mace. I'm from Los Alamos National Laboratory. And years ago, Bill Wilson at DITRA had asked us what could be going on. And at that time, I had proposed a mechanism that depended on quantum barriers and getting the quantum mechanics right. And the basic idea was, you know, in any metal lattice like this, you're going to have cracks and those kind of defects where you have particles caged in close proximity. Okay, and so what we did is we dumbed it way down so we could solve something analytically, basically. So we created a one-dimensional chain, and instead of modeling the full Coulomb barrier, Yukawa potential hardcore repulsion, all that, we replaced it with just step functions that were reasonable. And I went to the theoretical division of my place, talked to experts about what those energies and extents of those barriers should be. When you model that quantum barrier problem using a transfer matrix approach, you end up with these transmission lines through a one-dimensional chain where it'll breach the whole chain. And that's standard quantum mechanics. And so I think it's well known, and it's just an acute application showing that this kind of thing is possible from a quantum mechanical point of view. The part that we didn't get a chance to develop or present is the second half of the problem, which is the Hilbert space problem, right? So when you talk about a particle-particle interaction and the quantum chromodynamics associated with that interaction, that's much different than the wave function of an incoming deuteron simultaneously sampling a whole chain of deuterons in that transmission band. In fact, the Hilbert space for that reaction is probably orders of magnitude bigger than the Hilbert space for the particle-particle interaction, which means that it's probably not surprising that you aren't seeing really energetic neutrons or photons coming out of that system or other kinds of particles, because the number of possible transitions is probably much greater across that chain. But to actually solve that problem, I have been thinking about this recently again, because National Instruments has been prompting me to think about it again. And to properly solve that problem, I think you have to go back to the field theory equation, which Dirac originally wrote down the first version of that when he was 19 years old. And from that point of view, what people normally write down is an equation for a particle-particle interaction. They do a Taylor expansion of that equation. The terms of that equation are the Feynman diagrams in that interpretation, but it's for a particle-particle interaction. You have to rewrite that for a particle interacting with a chain of particles. You have to do a Taylor expansion of that interaction, and you have to ask what the terms of that Taylor expansion mean. Those are the nuclear transitions that are available to the system of the wave function for this particle interacting with the whole chain simultaneously. It's much more complicated.
I highly respect what you have just said. I have to confess that I understood about 30% of it. It's not your fault, it's me. I work for the stupid world of the industry. And I really highly respect what you said, and I'm sure that the gentleman in this room will be able to discuss for the next 30 hours about it. I am not interested in. What I'm looking for is acceptable engineering application of sound. It's data coming from a acceptable research. You have all the time of the world to find out the model, but the history of technology tells you that almost always we did things without knowing how the hell they worked. And again, I insist on that. I highly respect what you said, but what I really think we have to make an effort is to be a little bit humble, collect more experimental data, give me a couple of acceptable recipes. I will take the risk of making that damn manganese, which works once over 5 usually, and you never know why it doesn't work, but when it works, it has a wonderful taste. This is what I'm asking for.
And I know Dr. Akito wants to jump in.
I think he's very right and interested in the idea. And I'm also interested in what's going on in Los Alamos. If people are doing this kind of theoretical cold fusion in Los Alamos, that thing itself very interesting.
I will come to visit you.
And I have to say more, because for doing a theoretical modeling of cold fusion reactions, we need to treat anyway many body systems, not necessarily two particles, two hadron, but including other hadron and even lepton and so on. So we have to solve the quantum mechanical problem in many ways. And finally, we have to formulate the transition matrix, of course, to have a reaction rate.
Now I'm down to 50%.
We have many ideas and approaching process for that. And if the people who did the nuclear physics theory in the past who believe that maybe we can convert some proven theory and change something, modify and to apply the system and to elucidate. And however, the people who didn't have experience in nuclear physics in the past, they are brave enough to introduce a quite new idea.
Yes.
That is also, I think, possible, but we have no proof.
Yeah.
So we have very many approaches.
And I think this is a wonderful example of just the vast number of very intriguing physical theories for the origin and what it may be. And again, where those make experimentally tractable predictions, again, applying the scientific method is the key to understanding mechanism. But since our audience is so diverse, if I could humbly kind of take the moderator's prerogative and try to encourage, again, because we could, I'm a physicist, I'm fascinated by the models, but maybe kind of diversify the discussion more into other aspects as well.
I have a question. Could you describe briefly what's going on in that? Oh, sorry. My name is Mark Garnett. I'm a lab developer here for conference. I work on air conditioners normally. I'm in physics, so I find it's very interesting. Could you guys describe just briefly what we're seeing with the experiment downstairs? How is the experimental apparatus set up? How does it work?
Excellent point.
Not me. I told you I don't understand that stuff.
Well, we have the inventor in the audience to respond. That's a great
Okay.
question.
This one, sorry for the English, I am Italian. So,
Again,
the second point, we have done recently an experiment starting from some basic points. The first one was to find a material cheaper than palladium. Second one, don't use deuterium because expensive and other reasons. Third point, we have knew before some good result using nickel. We try nickel with some coating, and once we get wonderful results, up to 900 Celsius and 26 watt with energy density, power density as large as 1,800 watt per gram of nickel. Wonderful. For 5 days, we start everything. The wire broken in depth, no able anymore. But this gives us, we're sure something wonderful can be done with nickel. So we concentrate with nickel. Pure nickel, almost really, we know we were not able. We know we need nano material, nano something. So the K is nano. And we try to mix our old experience using wires and electromigration with nanomaterial at the surface. So we developed a new compound made basic, intrinsic, is very cost, commercial material is Constantan from Germany company, and at the thick surface of nanoparticles. The number per layer is about 1,000, really big number. We tried this material before with inert gas, argon, and helium, nothing happened. We use hydrogen, and we found that when we overcome some critical temperature, as large as 125 degrees, the resistance, instead of increasing, as expected, drop so largely, value before 10%, factor 20, 30%, and almost immediately start some excess power. This excess power increase spontaneously, just waiting the time, and spontaneously the resistance ratio decrease. So we have two effects at the same time that you cannot explain. First one, decreasing of the resistance, increasing the temperature due to hydrogen absorption. The second one, anomalous heat that we want to use. Something just like that. And one point very strange, we take off hydrogen, my origin is nuclear, use deuterium isotope, and we found small emission of gamma, before nothing, never, small emission during the loading time, and at the beginning of days, the reaction was endothermic, so lower than calibration. After a long time, go to zero and positive. Similar effect was found independently from Takahashi group in Japan, using some material for several aspects similar. So it means the copper nickel alloy, in proper dimensionality, has some good possibility to be used as practical device. So it's just like that. Now we to know how long it works, stability, okay, several things. But seems a starting point, using low-cost material and nanosurface, as thick as possible. A finish.
Very good. I mean, very exciting. I think, is there another question or comment? Very interesting work. Yes, sir.
I don't need a mic. I can just talk loud enough. My name is Daniel Plott.
Voice! Love!
I'm an intern here at National Instruments. I go to the University of Florida, and fusion is kind of a side interest of mine. And I was kind of curious if the Navy gentleman, I'm sorry, I forgot your name, if there was a way to find a description of the experiment you had with the palladium-coated cathode and deuterium.
I told you it would be one.
Yeah, the CNR, LENR, actually there's an LENR-CA website that has several thousand, its library has several thousand publications in it. So I think most of what you're looking for will be there.
Thank you.
Very good. And I think Stefano had a question.
But just a minute, let's help him. Which years were they? You know, 7,000 publications.
Oh, well, you can look by author, you can sort by author. In the case of code deposition, SPAWAR, SSD-PAK is the principal author in those.
Many of us find LabVIEW quite a platform for these kind of development system. Stefano.
First of all, thank you for your explanation. And I would like to change gears, not very technical, it's more dream. Do you think that there is any potential industrial application of these experimental data? Is there a business model that can be built around this phenomenon?
Maybe go to Alex instead of the panel for an answer.
Hi, my name is Alex Xanthoulis. The company is Evoked. I'm the CEO of the company. I'm not a scientist. Okay, I have to clear that out. So we see the whole thing on another picture. It's a different picture. Nobody has come out to say what's the benefits for the world out of this. Out of this LENR or whatever it is, wherever we want to call it. Now, our company has seen this project from the beginning as a project to the people and for profits, of course, I'm not saying. We have opened our technology, we have opened everything, receiving a lot of help, even from the gentlemen here without them knowing, reading whatever they wrote, and all the other gentlemen that are here. A lot of help from NI, and especially Dr. T has even helped us a lot, and a lot of other organizations in Europe and here. So I'm in the position to say that the Evoked has finished all the R&D about the reactor. We just need to get some materials. We work on nickel and hydrogen. Our reactor, single reactor, runs up to 5 or 6 kilowatt per hour. We are in the phase of, we saw it at the beginning as business. So we are a little more advanced than anybody else because everybody else sees us lab. From the beginning, what we care is, number one, do we have excess heat? Yes. Number two, do we have any dangerous emissions or something like this? No. Number three is, can we have it out of the people? And that's what we're trying to do. Now, I can say, and I can give you, because we know the costing, we know the cost of the power coming out, we know everything that we should know about this. Why it's good for the people? It's very simple. I will put it, because a lot of people care what they take out of their pocket, right? So, we say that one of the cheapest forms of energy is nuclear. Nuclear energy is between 4 and 5 cents cost, thermal. We believe that we are lower than half a cent. Okay, this is calculated, we can prove it. It's lower than half a cent. So you understand the innovation, what's happening to the world. Also, from the beginning, we were very open because we want this technology to grow everywhere. I am in a position to announce that we are talking to several countries that we will give our technology and they will produce in every country separately. This is 79 countries who are interested. Out of them, we signed with 6 final agreements, which goes next year. So, first thing for the development of this technology is all the people will get something like this. Poor people will get something. It's cheap. It's cheap. And it's a very peculiar. I'm from Greece. You understand that we were running more because we needed to give to people something. Okay? But the whole world is like this. Europe is like this. United States is like this. So that's why we expanded. So we have 2 directions, as I said. One is to establish factories next 5 years in 79 countries, 15 years. I don't know how long it's going to take. We cannot say anything about that yet. That's number one, that they will produce for the country independently. On the other side, we have a lot of companies. You can take the list of, I cannot open up names, you understand? You can take the list of the 100 biggest companies in the world. Half of them, we're talking about joint R&D in order to see for their use how they can use this technology. Now, I cannot answer you scientifically what's happening. We have a technical presentation, but from our technical manager tomorrow, we will open all our cards. Of course, we will hold our industrial secret. Forgive us for this, because this is the money that I was saying before. Okay, if we give this, there is no money. So, first of all, tomorrow, whoever wants to attend, we will have a full technical presentation. The results that we have is very high COP, okay, which can be industrialized. Also, each reactor, single reactor, goes up to between 5 and 8 kilowatt per hour. And I repeat, the cost is less than half a cent per kilowatt hour. Less. So, first of all, I want to thank Dr. D for the trust that he showed us up to now and the big help he gave us. Everybody here, because, listen, we stole a lot of things. We were reading their papers, we were reading their announcements, we were keeping silence for a long time. So everybody helped us with this. Of course, we don't have an explanation. That's what the gentleman said. We don't have an explanation. But also, we were based in our own financing. We never received a loan. We never received money from government or anything. Otherwise, we would never finish. They know it very well, if we were based in this money. So, that's the case. We are happy to announce for the first time in the world, we are ready, we are proceeding. We hope, if everything goes okay, because we're studying materials now, it's a matter of materials, to have something ready before 6 months. We believe that at the end of the year. And this is the reason we are moving from Greece, because of the economic situation, to Vancouver, Canada, our basic R&D, and we also move in Zurich for European R&Ds, and Melbourne for Pacific Ocean. That's all I can say. We are on the move.
Well, thank you. And this, again, heightens the interplay between more basic research, outstanding, more basic research, and the more applied translational effort of commercialization. Again, certainly both proceed in parallel, and it's very natural.
Can I just say something for the sake of the students here. It is not true, even if many people do say that organizations and companies do exist in order to make profit. It's not true. I will challenge anyone in this room to go down to a factory floor where you have a couple of thousand blue collars and motivate them, telling them, you know, you have to work 8 hours a day because I have to make a profit. Forget it. The reason why organizations do exist, companies do exist, is to create wealth. And if you create that wealth in a virtuous way, over time, continuously, a statistical indicator will be profit. Don't forget the Enron case. They showed very nice profits. But they are revising their budgets now in jail. But anyway, so the point is that the reason why companies do exist, the reason why industry does exist, it's because they create that wealth. It's an old story. It's the fundamental of economics. Never forget that. So nobody, especially not in this field, is thinking to grab the idea, what I call the vulture capitalism, or the vulture capital, not venture. Get the idea, establish as fast as you can a monopoly as strong as you can, and dominate the world. This is Pinky and the Brain. Right? Now, point is, maybe we're not geniuses, but for sure we're not insane.
Very good. We might go to a final question here in the back. Unfortunately, we're coming towards the end of our hour.
Yeah, thank you. I have a question for the panelists. In the experimental data and results that you've seen, what's the range of ratios of electrical energy in to thermal energy out? Because as I understand the experiments, that's what's going on, right? You put in some electricity, you get excess thermal heat. If I'm mistaken, I apologize.
Maybe I can speak to that. It's this wide range, and fortunately that power factor has been improving with time, making the experiments easier to do. But one experiment, actually performed by a gentleman in the front row here, Energetics Technologies in Israel at the time, performed an experiment in which 40 kilojoules of electrical energy was put in, 1.14 megajoules of thermal energy came out. So the power, that energy out over energy in for that defined period from the initiation of the experiment is about 28 times. I must say that I've done many, many experiments, and my group has done many, many experiments in my laboratory, seeking a goal of 28, 2,800%. We have not seen anything, but we do see effects of 200, 300, 400%, to 2, 3, 4, 5 times. I think to properly commercialize at the temperature levels that we're seeing, you'd need a gain of about 10, for example. It was a round number. But that is achievable. I think the gains have been as small as they have only because all of the material present in the reactor was not participating in the process at the same time. And that's an engineering skill. First thing was to prove that there was an effect. Second was to demonstrate the conditions under which the effect was observed. Third thing is to scale it for two reasons. One is to make it much more easily observed and requiring less sensitive instrumentation. And third is the potential for taking this to some commercial end objective. And this is one case where, I think most cases are this way, where engineering and commerce is leading science. You know, the strongest statement I've ever made about the potential to commercialize this effect is nothing in my research has indicated to me that there would be any impediment to making a practical heat-producing device out of this. So I know of no reason why you couldn't scale it up and do exactly what the gentleman from Greece just spoke about. So I don't know any reason why not. He doesn't care. Why not? I'm doing it, okay?
Can I add electrode method at room temperature. We don't have any nominal input power, input energy, but we have only output energy. So the gain is nominally infinite. However, for elevated temperature, elevated condition, we need to heat up the system, so we need input energy. And in that case, the output energy ratio depends on how much reacting sample we use. So that depends on external condition. So once we see the excess energy in the temperature elevated condition, we can improve and increase the output by adding sample more and more, and then scaling up the system. In that way, it goes and approaching to the industrial application.
Outstanding. Maybe if we could go to Dr. T.
Sure. And since I mentioned Peter's work in my talk, I think we need to say a word or two about what he's been doing in his latest results. Otherwise, I leave you guys hanging without an answer.
I've been known to go on for hours about theory.
You got an airplane tonight.
That's right.
McKubre's had to sit through quantum theory discussion at 8:30 in the morning, Sunday morning, in this group that went on for hours. But I'll try to be brief. The basic idea is that my models are based on a coupling between vibrations in the lattice and nuclear excitation, which is a relativistic effect like spin-orbit coupling. And we hadn't appreciated it. I have a model now that works that way. It's posted on the Los Alamos archive, so you can download it and see the very latest version of it under my name. But the basic idea is if you start out with, say, a metal, and you ping it, so you put in some vibrations. Maybe the vibrations are 50 to 100 megahertz. And if you have the right nuclei in it, the one with the lowest excitation energy is at 1500 volts in mercury to 1. The idea is you can transfer energy from the vibrations to the nuclei. And you can figure out that you've done that because they radiate. And in an experiment done in Russia that I'm very interested in, the radiation is collimated. It's directional. And that's very interesting and unusual. And that's also consistent with the models. Anyway, the same models provide foundation for excess energy production. And there's a number of predictions they make that can be tested. My hope is that in coming months and years they can test them, see whether it's right or see whether it's wrong. There's a very large number of models out there. And we're going to need some experimental feedback in order to figure out which ones live and which ones die.
Wow, thanks a lot. Well, unfortunately, we're coming to the end of our hour, but to, again, build upon the scientific method, and again, Peter's theoretical accomplishments now, looking for experimental tests. We've only been in this game for half a year at the University of Missouri. I'm extremely impressed by my colleagues who have been making great contributions over the last number of decades, really outstanding. But one thing that really excites us is, again, expanding the parameter range using, say, scattering, neutron scattering, X-ray scattering, to kind of query at the atomic level what these surfaces are doing and bring them under direct control. So I think that, again, this will be the subject of what we do going forward, and I'm sure the material for many, many more very, very useful conferences and discussions in the future. Stefano, would you have something to close us with?
Yes, I would like to clarify a few points from a national instrument perspective. We will never do confusion per se. We are instrumentation and control to both. So we are here simply because we believe and we prove that the National Instrument Graphic System Design approach is applicable for the theorists. So LabVIEW can be used as a mathematical tool, a mathematical model for the theories that the scientists are elaborating. And so we've been working with the university. We hope to be able to work with Peter and MIT and other institutions from a theoretical standpoint. And of course, there is no theory without having a good explanation. And LENR is as all the tools with our example this is our interest in this science as in many other sciences. And we are very happy that we were able to bring all these people here and to move forward with the scientific
Can I just, Stefano, can I just add something? See, what's really interesting, exciting in this problem, this issue, is that it cannot be tackled if not by a extremely broad multidisciplinary approach and competences and knowledge. So it's not the domain, it's not something that the physicists have to play with. It's not something that, it's not the feud of the chemists. That's not the case. If we aren't able, we at industry, to tell those who are gathering the data, what kind of data we need in order to make up our mind and look at this issue as an opportunity and not just a pure risk. If the scientists are able to tell them and I what kind of instruments they need, what kind of specs, what kind of precision, we're not going forward very fast. And the other thing I really have a need to share with you, don't think about future application with logic or the experience we had in the past. It's no more the case that we will have the dominant solution.
Right.
It's not going to be the case that we're going to use this only because we want a 10,000 megawatt plant. Maybe we're going to have, this solution will be good for 200 watt plant, 3 kilowatts for your home, or 10 kilowatts for a desalination plant, whatever.
Perhaps heroin.
Whatever. That's not the point. I mean, we have to start to think in terms of new architecture, new solutions, more complex, more beautiful, and especially much more fun.